8:30, 8:45, 15 minutes before, just to iron those things out. So a question for all of you. Friday, should we begin at 8:45 instead of 9?
Yeah.
So I just want from all of you, so there are 29 participants. So if you don't say anything, I'm going to assume that you are okay. Is that the way it goes? So you can do the thumbs up or something like that, but Jezebel, why sure with the question mark? You don't have to. I'm just saying that, I'm going to give you the code. I'm just going to count 60 minutes. All of you are there maybe at 8:50. We have got responders down. We've got everything down. Then I'm just going to give you that time, just start, and I will stop you 65 minutes. I just about the difference is this, that we iron out that responders and everything. And if everybody's ready, and that means you get 5 minutes more. Because I want to stop at 10:10. I don't want to go beyond that because some of you have classes. So if it means 5 minutes more to you guys, take 5 minutes more. Does that make sense? Okay. Ready for today's lesson then? By the way, I don't think I'm going to assign any, maybe new homework, but with 3 or 4 problems, but this is all due Monday. So the last homework that you saw was again due Monday. So let me just remind you what chapter 8 was about, at least what we did. So chapter 8, it's again applications of integral. So we set up the integral to find arc length. I think I have made it, William, 10 minutes per question. So I think I've made them 6. Maybe you won't need all 10 minutes for each question, but that depends on your algebra speed as well. So set up the integral to find the arc length. I'm going to say there are 2 versions. This one, version 1, version 2. And then you have number 2, where you set up the integral to find surface area. Please do not confuse this with area under the curve. Because what we did before was area under the curve, area between curves. I'm going to remind you that this was the area. I'm going to remind you that this was the area that you found. So why is this not the surface area? Because this is not a 2-dimensional, sorry, this is not a 3-dimensional figure. It's not a surface. It's just kind of, it's in 2 dimensions. So what do I mean by surface area? Oh, you get this surface by revolving a curve about a line, which we're going to keep very simple. It's going to be x-axis or y-axis. So you're going to get this 3-dimensional object first. So in other words, this was area under the curve. Surface area is going to be this one revolved. So you get something like, and I'm trying to see, so you are going to get something like this, and you're going to get this solid of revolution, so to speak. And you are supposed to sort of paint this one. So you are supposed to find the surface area of a solid of revolution. So I'm just going to have comments here, and you can go and ask questions if you have that. So what do we need there? So we said, when we are talking about a surface area of a solid of revolution, I'm just going to start this one. So here was our curve. And then we are revolving it around, say, the y-axis. And I'm going to grab that. And so you are going to have this sort of And so the solid of revolution is going to turn out to be something like, sorry, it's going to turn out to be something like that. And it is this guy that you want to paint. So we said for this one, this formula, surface area, is integral C to D 2 pi. We need the radius times the arc length. So that's the general formula. So tell me, if you're going about the y-axis, if you're going about this one, radius is, so if we're going about the y-axis, radius is, as you see it, as you see in the picture, the radius is going to be some, I'm going to say x. So this is going to be 2 pi x. And then arc length, I have a choice. I could go with version 1 and I could go with version 2. So I think it's time for example. So let's do an example. So again, I'm going to emphasize for surface area, sorry. So for surface area, the components I need are 2 pi radius. This comes from the axis of revolution or rotation. So this comes from the line of rotation. And times it by arc length, which we said we have version 1 or version 2. So what do I mean by that? So here we go. Here's my first example. So we are going to find the exact area of the surface. And these are the key words. So you're finding an area of the surface, not under the curve. By rotating this curve, sorry, this is not the way. This is not the example. So 9x equals y squared plus 18 about the x-axis. So I'm going to start the solution. So good, Trent, I've got that from you. So here we go. Is everybody ready then? And so we are, you are rotating this region about the x-axis. X is between 2 and 6. So decisions to be made. So I'm just going to say, because x is between 2 and 6, I choose this version. So I'm just going to write this. 2 is less than x is less than or equal to 6. So I want to work with this version, which is 2 to 6, 2 pi. I'm going to worry about the radius later. So it's going to be radius. But the arc length is what I'm talking about. And because this is x is between 2 and 6, I choose to integrate with respect to dx. If I choose to integrate with respect to dx, then for the arc length, I have to use this version. Agreed. And I just want a thumbs up or something. Very good. And so because you are talking about this, then the first thing we've got to do is we are going to look at that equation. So, okay, if I want to use this version for arc length, then I notice it is given to me as 9x equals y squared plus 18. This is the equation of the curve that's been given. So I will have to solve this for y. So I'm just going to say this is y squared equals 9x minus 18. So I'm just going to take a look at the chat. So yes, William, the radius would be the curve f of x. But remember, the radius, because you're going about the y-axis, this radius is going to be some y. And y equals f of x. You're absolutely right. But we are here, we're solving for y. We are actually getting that y equals f of x. So y will be plus or minus square root of 9x minus 18. Tell me which y to pick and why. One is the alphabet, one is the question. So tell me which y to pick and why are we going to do that? So y is going to be positive or negative? So which part would be? So very good. We're going to pick y equals positive, exactly about you and Karen. So you are right, Karen. So I like how you talk to yourself when you're here with us. So you are right, because you're going to say when x equals 2, the value of y is going to be 0. When x equals 6, y is going to be positive. So in this interval, this y is positive. So I ignore the negative. And so I'm going to work with y equals square root of 9x minus 18. And now we start. Remember the integral here. So I'm going to set up the integral first. So the integral here is 2 to 6 now. 2 pi. The radius, you agreed, because we're going about the x-axis. The radius is y. But because I'm integrating with respect to dx, I'm going to write this radius as square root of 9x minus 18. And the other bit is 1 plus dy by dx squared dx. So I'm going to compute this. I'm going to get this one ready as I did with arc length. So I want to get this ready. So I'm just going to work on this part. So here we go. So y equals square root of 9x minus 18. If we want, we can box this, because you know we are going to come here and put everything in here and integrate after. So dy by dx is 1 over 2 square root of 9x minus 18 times 9. So dy by dx squared is going to be 81 quarters. You don't like how I'm writing this? You can write 81. So what did I do wrong here? Point it out, please. So this was dy by dx. This is a very intentional thing. So if I'm squaring this one, what should I write here? Very good, Karen. I didn't square the radical, so there's no radical. So this is just this. So remember, I'm getting this one ready. So this is just a square part. Now I'm going to add 1 to it. So I'm going to say, okay, dy by dx squared plus 1. I'm going to use my own trick. It is 81 for 9x minus 18 plus 4 times 9x minus 18. I'm going to pause here. Do you see what I did there? Because when I add 1 to it, what do? I just use this as 1, isn't it? We just use the denominator as 1. So I'm going to pause here and wait for any questions. So anything? We're okay?
So far, so good.
Okay, great. So we are just going to then take care of business up on the numerator, which is 81 36x minus 72 over 4 times 9x minus 18. So that gives us 36x plus 9 over 4 9x minus 18. So I'm going to say, okay, dy by dx squared plus 1 seems to be, you are going to check if I'm doing this right. So I'm saying this is going to be 9 quarters 4x plus 1 over 9x minus 18. And now I'm going to go to the box and I'm going to say this was 2 to the 6, 2 pi. The radius was square root of 9x minus 18 times 3/2 square root of 4x plus 1 over square root of 9x minus 18 dx. And are we okay there? Because remember, in the integral goes the square root of this. And we okay? Cicely, I'm going to answer your question. I don't need to you can simplify the denominator but you would notice the denominator gets cancelled with the radius. So once I saw that denominator turned up like that, and I already set up the radius to be square root of 9x minus 18, I saw no value in sort of simplifying it.
So, did you square root? You already did the square root for the 9 over 4
Correct.
and the 4x.
Yeah, so the numbers were squares, so I already did the square root, which was 3/2. Just the square root of the top, which was there, and the square root of the bottom.
Got it.
Okay. And so now we can cancel the 2's, we can cancel, it's not so bad. Okay, so this turns out to be 3 pi integral 2 to 6 square root of 4x plus 1 dx. And I promised you that neat little trick. If you have latched onto it, then it's going to help you so much. So now to integrate this one, we're going to say what? 4x plus 1 is u, 4 dx is du. So I'm going to say this is 3 pi over 4 box to box square root of u du. Which means when I finish my integration, and I'm going to just go and jump a little ahead of this one. So when I integrate, I claim I get this 2/3 4x plus 1 to the 3/2 from 2 to 6. So I'm going to do that dot, dot, dot. So if you want to write something in between, just go for it. But I'm going to pause a little bit, but are you here with me? Do you agree? And I'm asking about this step with the arrow. So in between, write whatever you want to write. So no questions? Are we okay there?
Yep.
Great. So then we just cancel whatever you need to cancel. So it seems you have pi over 2. And now my trick, because when it is 3/2, this is going to be what? 25 to the 3/2? Minus, this is going to be 9 to the 3/2. Remember the trick, we said pi over 2, so this is going to be 25 square root of 25 minus 9 square root of 9, which is going to be pi over 2, 25 times 5 minus 27, which is pi over 2, 125 minus 27. That gives us what? 98 pi over 2, which is 49 pi. Are we okay there? And then I want you to take you on a ride for some other problems which I see have worth in them. We okay? So I don't see any questions. And when I was in, okay, are we ready for one more example at least? Okay, so I'm going to take this up and let's do one more example. So here's example 2. And for this one, I just want to jump up a little bit ahead and see if we can do this one. So here it says, find the exact area. by rotating the curve. I want to see how you would handle this one. I lost my own problem. It was a big problem which I wanted to do. Yeah, so let's go with this one. So x equals 4 plus 2y squared. 1 is less than or equal to y, less than or equal to 2 about the x-axis. Yeah, about the x-axis.
How does this differ from what we've already done?
And you tell me. So go back to the problem that you see there and tell me what is the difference between the two. Great, William. So what was the difference? So you're right. Let's point out the differences. So here you were given x is between two constants. Here you are given y is between two constants.
Right, but this is asking for the area, not the surface area. So wouldn't we just be
Oh,
finding
no. Exactly that. I'm so happy you caught on that. So when I say exact area, because it is rotating the curve, this rotating the curve gives you a surface, Russell. So when I'm asking area, I'm asking area of the surface. In other words, the area of the vase.
Oh, and then if you were to say volume, you'd be asking for the other value.
Right. The volume is something that you can stuff your vase in, isn't it? That how much material can I stuff in there? So when I'm asking the volume, I'm asking you the capacity. When I'm asking the surface area, I'm asking you to how much paint would I need if I was supposed to paint this?
I see.
So here, I'm just going to point out that y is between 1 and 2. What does that do for us? And we are going to say, okay, so the arc length, I'm going to use this version. And so if I set up the integral, I'm going to say this is going to be 1 and 2 pi, radius, and the arc length.
And
Now
so
a question for you. Yeah, go on.
the radius would be x in this case?
So you are going about the y-axis. So if something is going about the y-axis, then the radius is
X.
So let me draw that picture for you. So if something is going about the y-axis, now this is x equals 4 plus 2y squared. So let me say, you know, x equals y squared is going to be something like that. Y is between 1 and 2. So I'm just talking about, sorry. So I'm just talking about this kind of thing. Sorry again. So it is this kind of thing. X equals y squared, meaning if it's not y equals x squared, so it's not this parabola, but it's this one. This is not the exact one, but I'm saying this is it. Now, if you're going about the y-axis, oh God. So if we're going about the y-axis, Russell, sorry, the x-axis, the radius would be?
Y?
There you go. So the radius is y. So now I'm going to say, okay, I've got the radius to be y. I'm integrating with respect to dy. So tell me, people, do I need to mess up this y then? Just like I did in the other problem. Here the radius was y again, right? Because you were going through about the x-axis, the radius was y. But you had to write y in terms of x, y, because you were integrating with respect to dx. But here you're integrating with respect to y. And that's the point I wanted to make. So will you write this y in terms of x? And the idea would be?
No.
Very good. The answer would be no. So I'm going to box this again. And I'm just going to start this one. This one is not going to be so bad. And look how easy it sort of becomes. So now you're saying, okay, x equals 4 plus 2y squared. So dx over dy is just going to be 4y, right? So dx over dy squared is just going to be 16y squared. So dx over dy squared plus 1 is just going to be square root of 1 plus 16y squared. And I'm going to pause, right?
So in this case, you're not doing that little trick of making 1 over 1 with the 16y squared?
No, because there was no denominator. See, when do I use that trick, Russell? And you're asking very good questions. So when do I use that trick? When I have some kind of denominator. Here I didn't have any denominator. This was dx over dy squared. We just had to add 1 to it. So we added 1 to it, which was just adding 1 to it. And then we took the square root. And this is what is supposed to go in your integral. So I'm just going to say this time it turns out to be integral 1 to 2 pi y square root of 1 plus 16y squared dy. And Karan, I'm just going to point out to you that I want you to see, if you're writing, then you already see that. But these are the comments I made in the last example. X was given between 2 and 6. So I'm going to say this. This was the difference from the last example to this one. So X was between 2 and 6. So we said we are going to integrate with respect to dx. If you said we're going to integrate with respect to dx, because you were going about y-axis, the radius is y. But because you are integrating with respect to dx, now you're telling yourself, I have to write y as a function of x. And Karan, I'm just talking to you. So is that, are you with me? Are you listening as I'm answering your question? Okay, so now let's keep this in mind. And now let's get to the problem that we are doing right now. So what was given to us here? That y was between 1 and 2. So we decided we're going to integrate with respect to dy, because that's the easiest in terms of arc length. And then we are still going about the x-axis. So the radius is still y. The only thing is the technicality now. I do not need to write this in terms of x. I just could keep this as y. And that's it. So did it clear that up? And that's why I took this problem that I took right after the first one, because I wanted to point these things out.
Is it just y, or should it be 4 plus 2y squared?
Again, when you are saying it's 4 plus 2y squared, that is the x value, isn't it?
Correct.
And you saying, because I'm going about the x-axis, the radius is y. See, the things that I think I'm going to write that. So here are the comments I'm trying to make. If anything is rotating about the x-axis, any curve, then I know the radius is going to be y, because we put it here and we rotate it like that, isn't it?
All right, yeah.
Right, so it's going to be y. So what is the difference here? The difference here is when I'm computing, so when I'm computing the surface area, it is the arc length, the version of arc length that I use, that decides if I'm integrating with dx or dy. So let's talk about this one. So if we are going about the x-axis and I'm going to integrate with respect to x, then I have to make sure that this radius, which you agreed with me, is y always, has to be written in terms of y equals f of x. If I'm using this version of arc length, and you still agree with me, if we're going about the x-axis, the radius is y, then I do not need to write this in terms of x. I'll be okay there. So Karan, I want something from you. Does that make sense? And maybe as we do more problems, you will get it. So the idea is, do I write the radius in terms, and we could do it the other way around as well. So I want to say this one as well as I'm completing this. So if we are rotating something about the y-axis, I'm going to say this is whatever that is. So if we're going about the y-axis, then you agree the radius is x in each case, isn't it? And then the same thing, when you are computing the surface area, and I like to play with this one, so I'm going to grab my brush. Here it is. So here is that. So here is that surface that you generated with this one. So when I'm talking about the surface area, sorry. So when I'm talking about the surface area, the component in surface area is arc length. So again, I'm going to decide arc length, do I use with dx or with dy? Remember, you're going about the y-axis, so you know that the radius is x. So if I'm going to use the integration with respect to dx for arc length, then I just keep the radius as x. If I'm going to use this one, then I need to solve or write x. I'm not going to say solve. I need to write x in terms of y.
So,
and I'm just going to say this before I take your questions. So if you are questioning what just happened here, or you're saying the radius is y, and y is somewhere between 1 and 2. Here you said that the radius is y, but you wrote y in terms of x because this one was there. And then you are saying, oh, this radius is somewhere between y equals 0, because that is the value. If you put 2 in there, then you will get y equals 0. And when you put x in there, you will get something else. So y is between these two constants, 0 and something. But you are just writing y in terms of x, that's all. Go on, Russell. Say what you got to say.
So if I'm understanding you correctly,
yeah.
Basically the y value is a value, right? It's 9 or 10 or whatever height. And we need that number anywhere along this curve for the surface area. And if we're doing it in x, it spits out a y value if we write y or x in terms of y or y in terms, right?
Right. So if I understand you correctly, I'm just saying this, that if y equals x plus 3 and x is between, say, 1 and 2, then you would agree that y is then between 4 and 5, right?
Right.
So the only thing is, if I'm not solving for, I'm not putting y in terms of x, then I should see y between 4 and 5. If I'm putting y in terms of x, then the bounds of the integral should be between 1 and 2.
All right, I get it. Thank you.
Because your y varies. Any questions about this one? So any interest in finishing the problem? Because the integral is very, very easy. Because, you know, this is going to be what? 1 plus 16y squared is u. So 32y dy is du. So I'm going to say this is going to be integral 1 to 2 pi. Oh, I should say empty boxes because we're not changing. So this is going to be 2 pi 1 over 32 square root of u du. Right? Finish this one. This gives us what? Pi over 16 times 2/3. I'm getting ahead of myself. Yes, 1 plus 16y squared to the 3/2 from 1 to 2. So I'm going to copy it way down there. So a question for all of you. Should I erase this thing in between, this thing, this chunk, or should I keep it for your notes?
I'd like it to be kept. It helps me understand the idea.
Okay, so Karan has the same thing then. So I'm just going to put it in a box, the sort of the red lines, because this was just the conceptual part of it. So this was just conceptual part. The problem is going to continue down there, So I'm just going to leave the you and everything to you, but I'm just going to say this is where we were. And y was from 1 to 2. And so we have what? Pi over 24. I'm going to use my own trick, so 65 root 65 then, minus 17 root 17. And any question? Okay, so Joshua, what happened to the radius y? It is still very much there, but we used to integrate, we used the u sub. So pay attention to this one. And then y du, yeah, y gets cancelled out. You could say it that way, but for me, y dy is du over 32. So this is du over 32. Okay. So anything else? Should we do one more, or should we go on to the next section?
Can we see one revolved around the y-axis?
Okay, let me find one. So here we go. Let's see if you like this one. And this one is without numbers. And let's see if this sits well with you. So here we go. So here's example 3. So x equals square root of a squared minus y squared. 0 is less than y is less than equals a over 2. And this given curve, so this curve, is rotated about y-axis. And find the surface area. It says find the exact area. So I want to say this. When it says find the exact area of resulting surface, translation, find the surface area of the solid. I want to remind you, this is from chapter 6. So if you have a curve which is rotated about an axis, that gives you a solid of revolution. So this is from chapter 6. When it is asking you area, you can say to yourself, oh, I'm supposed to find the amount of paint needed to paint this thing. And this is the surface area. So start this one then.
All right. Well, I'd probably sketch a quick 2-second graph myself.
Okay.
Just to be able to look at it.
Okay.
So it's going to be basically a x and y axis with a basic square root graph curve.
Correct.
And then we're revolving it around the y-axis.
Great.
So,
I'm going to start from there. I'm going to say the way I did it was this thing. So I'm going to go with this one. So 0 is less than y is less than or equal to a over 2. That means I'm thinking, oh, I should go with this version of arc length. Right?
right.
Meaning I'm integrating with respect to y. Okay. But you are going about the y-axis. So if we are going about the y-axis, the radius has to be x. So I'm thinking this is integral 0 to a over 2, 2 pi. The radius is x, and so on and so forth. So now a question to you. Should I leave the radius as x, or should I write it in terms of y?
Write it in terms of y.
Very good. This is what this one. So what is a here? I'm going to say a is a constant. And now, so we start. So this is going to be 0 to a over 2, 2 pi, square root of a squared minus y squared. And I'm going to copy this down because I want to get this ready. And this is the box. So this is where I'm ready. And this is where I start working with that integral. So we have x equals square root of a squared minus y squared. So dx over dy is going to be 1 over 2 square root of a squared minus y squared times negative 2y. Right? So Karan, I'm just not answering your question because I give you a minute and you answer your questions yourself. So I see, oh, never mind. Yeah, so so don't be under the impression I'm trying to ignore you or something. It's just that if I give you a minute, then you figure it out. Okay, so when I square it, then I'm going to get y squared over a squared minus y squared. And I picked this for two reasons now. Russell, the question that you were asking earlier, now I want to add 1 to it, right? And when I want to add 1 to it, the way I use this, the trick I use, I just take this denominator and I say, I'm going to think of this 1 as a squared minus y squared over a squared minus y squared. So I don't have to do too much algebra. And so I'm saying, okay, this dx over dy squared plus 1 turns out to be y squared plus a squared minus y squared over a squared minus y squared. So that will just be a squared over a squared minus y squared. Remember, this is the part that goes under the radical. So I'm going to go back to this one. Remember, this is just this. It goes under the radical. So I claim that integral turns out to be 2 pi square root of a squared minus y squared times a over square root of a squared minus y squared dy.
Can I ask a quick question for the step right before that?
Sure.
So we have a y squared multiplied by a squared minus y squared.
Not multiplied, added.
Oh.
Because it's plus 1.
Got it.
Yeah.
That answers it. Thank you.
Okay. So this gone then. And wasn't this the easiest one on the planet? So this is 2 pi y. Ay, sorry. Because a is a constant. So this is going to be 2 pi ay from 0 to a over 2. So this is 2 pi a times a over 2. So this is going to be pi a squared. And let's check if we're right. So I'm going to wait for that check. Any questions before that? So here's the screen. I don't know how you're writing, how far you are, but I see no questions. So I'm hoping you all are okay. So any questions? And Baldev, I hope you're writing this time. So I don't see any questions. Okay.
I think so far I'm all good.
Okay. So now let's look at the problem itself. And it was very interesting, Russell, when you said you wanted to graph. And if you notice, I never commented. I didn't say a single word because you were on to something. So, and I thought you would crack that problem and you would say, oh, you know, I can answer this right now. But here we go. So x equals square root of a squared minus y squared, right? So let's recognize this curve. This was 0 less than y less than a over 2. So this isn't this. So isn't this. So isn't this part of the circle? What circle? This circle of radius A. So this is the circle of radius, sorry. Let me draw a better circle. So this tells me this is the circle of radius A. You were saying x equals square root of a squared minus y squared, which means it is this part of the circle. Why? Because x is positive here. So this is square root of a squared minus y squared. This is x equals negative square root of a squared minus y squared, because x is just negative here. So it is this part of the circle. Now, you said 0 is less than y is less than or equal to a over 2. So when we are talking about this one, the radius is a. So this is a, this is a, this is negative a, and this is negative a. Maybe I should write it in red. So this is a, sorry. And this is negative a. Agreed? And this is negative a. And this is positive a, because this is just the radius of it. So you said 0 is less than y is less than or equal to a over 2. So you were talking about this kind of region. So y was between 0 and a over 2. So you were talking about this region. I'm sorry. So you were talking about this region. Ah, okay. I'm grabbing the wrong things. So this is y equals a over 2. This is y equals 0. And it was this region that you're talking about. This was the one that was going about what? X-axis? And so what you were talking about when you get this one is you get this surface. This sort of cylinder. And then when you figure out the surface area of the cylinder, you would agree with what we got there. So is that good enough? So you wanted to, and Russell, you wanted to see it before, and I just wanted to kind of go back and show you that you can, you know, this is a over 2, so you can figure out the surface area of that one, of the cylinder, and it would come to that. Are we okay there?
Yep. That's actually kind of cool.
And that's why I said, when you said y-axis, I thought, okay, we should do this. So here is the last one that I wanted to do, which is going back to the last example, Gabriel's horn. So the last example, y equals 1 over x. X was greater than or equal to 1. This curve was rotated about the x-axis. And we found its volume. And the volume, interestingly, turned out to be pi, which was a finite number. Why am I saying this? Because I'm trying to say to you that look at what Gabriel's horn was. So this was your y equals 1 over x. So this was your Gabriel's horn. Maybe this time I should grab that brush. So this was your Gabriel's horn.
Professor?
Go on.
It seems a few people have questions in the chat about the previous problem.
Was it y-axis then? But you would get the same thing. So, curve is rotated about the y-axis. So let's do that. But it's the same cylinder. But it's not the same cylinder. It's a cylinder that you're going to get. So you're absolutely right. Let me fix that. And thank you about that. So this was rotated about the y-axis. So you would get... and thank you for pointing that out to me, Russell. I was so much in Gabriel's horn. I like that example. And so it is this cylinder that you're talking about now. Right? And that sits well now. Yeah? Okay. So let me go ahead and finish this one. So this one is Gabriel's horn, y equals 1 over x. And what do we want to do this time now? We want to paint it. So we want to paint it. Not that way. Well, it looks cool. But anyway, so here we go. So we want to find surface area. So going by our list, so we're going to say, okay, x is 1 to infinity. I'm going to say x is greater than or equal to 1. So the arc length I choose is dx. Oh, geez. What did I just do? Did I just lose everything?
Is there an undo key?
Where would I find it? Okay. There we go. It's back. It's back, people. The notes are back. So this is going to be 2 pi radius. And we're going to go with this one, isn't it? Right? So far, so good?
Yep.
So tell me, if we're going about the x-axis, then the radius is?
Y.
Very good. Do we have to write y in terms of x this time?
Yes.
Very good. The answer is yes. You will have to write y as 1 over x. And so with our token, I'm going to start with this one. So y equals 1 over x. So dy by dx is negative 1 over x squared. So dy by dx squared is going to be 1 over x to the 4th. Now we add 1 to it, which is going to be 1 over x to the 4th plus 1, which is 1 plus x to the 4th over x to the 4th. So I'm going to say this is going to be 1 to infinity, 2 pi, 1 over x. And I have here square root of 1 plus x to the 4th over x squared dx. Right? And we have lots of problems. This is not easily integrable. More importantly, I'm going to make some comments here. Oh, this is an improper integral. So maybe a better question to answer here is, does it converges or does it diverge? So is it converges or does it diverge? So I'm going to say, to compute this, I would have used limit as b approaches infinity, integral 1 to b, 2 pi, square root of 1 plus x to the 4 over x cubed dx. I want to point out to you that u sub doesn't work. So if you try to do it right now, u sub is out. It does not work. Trig substitution and all of that do not work. But more importantly, because it's an improper integral, maybe I want to answer this question first. So to answer that question, I am going to look at this one. And I'm going to use that comparison property. So I start here. X is greater than or equal to 1, right? Because we're talking about Gabriel's horn just starting like that. So I'm going to say x to the 4 plus 1 will always be greater than or equal to x to the 4. Agreed? Answering your question, Joshua, 1 over x times x squared is that x cubed. Sorry, Jonathan. So are you seeing what I'm trying to point out to you? That this was the integral. This is the improper integral. Yeah, okay. So I'm here. And I'm talking about this improper integral, really. So I'm just trying to build this. I'm just trying to see if this even converges, because if it diverges, then I know it's not going to be a finite number. So far so good. So I'm trying to build this up. So square root of x to the 4 plus 1 is definitely greater than or equal to square root of x to the 4, which is x squared. So what did I do here? Take square root of both sides. Why? Because that is what this guy looks like, and I'm talking about this one. So I'm going to multiply both sides by 1 over x cubed. Why that one? Because again, I'm building this structure. So I get square root of x to the 4 plus 1 is greater than or equal to x squared over x cubed, which is 1 over x. So far so good. So I'm going to point out to you, f is greater than or equal to g. So this is the little guy. And the one that you were after, this is the integral that you wanted, was the big guy. So tell me, what happens to integral 1 to infinity 1 over x dx? And I'm going to say it diverges, because if I remember, this integral only converges for p greater than 1. It diverges when p is less than or equal to 1. So if the little guy diverges, then what about the big guy? So by comparison theorem, so anybody ready to answer? So if the little guy diverges, then what about the big guy? Very good. So it diverges. So what do we mean by that? Oh, I did not need to compute that integral. Because that integral is infinite. So what about the surface area? The integral for the surface area, the integral diverges. Which means what? I don't know if it does not exist, if the limit does not exist, or it's infinite, but this is not finite. That is for sure. And so what are we saying? That this Gabriel's horn has finite volume. That means if you wanted to put stuff into it, the capacity of this one is finite. How much stuff can it hold? Oh, it can hold pi amounts of stuff, pi cubic amounts of stuff, because we're talking about volume here. But if you want to paint it, how much paint would you need? Oh, infinite amount of paint, undetermined. So not finite amount of paint. Is enough to paint this horn. And that is one of the paradoxes. That it can hold a finite amount of volume, but if you try to paint that, then it seems like you need an infinite amount of paint. And this is the one that I like, because it really, really gets math going now. It challenges you conceptually, which I'm going to need for sequences and series. This kind of intuition, this kind of thinking of finite and infinite, the kind of that infinity thinking, we're going to need it for sequences and series. And here it is. So here is a very good example of what's happening there. So I think we are at the end of the class, so I'm going to stop. So any questions, anything? So I'm just going to put it up in announcement, so don't worry. So I will at least start the Zoom meeting at 8:45. If all of you are here, I'm just going to give you the code. You're going to start the test.
Alrighty.
So these are my office hours. If